Welcome, my friends! In this video, we will be discussing an important discrete probability distribution called the Poisson distribution. The Poisson distribution can be used when the mean number of occurrences of an event is known within a certain time period, area, or other frame of reference. Time is the most common frame of reference used in the Poisson distribution. For an example relating to time, let's say that a hardware store knows that, on average, 5 customers enter the store in a 20-minute period. The Poisson distribution could help us answer questions like, what is the probability that 7 customers enter the store in a 20-minute period? Or what is the probability that less than 4 customers enter the store in a 20-minute period? Examples relating to time are the most common, but sometimes the Poisson distribution can be used in other circumstances, when an average number of events doesn't happen in some time frame, but in some amount of area, distance, or within some other applicable unit. A good example is to consider a book that is being edited. The book might have an average of 4 grammatical errors within a 50-page segment. We could use the Poisson distribution to answer questions like, what is the probability that 3 grammatical errors will be observed in 50 pages? Or what is the probability that more than 7 errors will be observed in 50 pages? In case 1, the event, a customer entering the store, occurs some number of times within a specified time period, 20 minutes in our case. In case 2, the event, a grammatical error in a book, occurs some number of times within a specified number of pages. In either case, the Poisson distribution can be used to calculate probabilities. Other examples like case 2, not related to time, include the number of pieces of trash found in a section of the highway, or the number of cracks in a specified area on a cement wall. We will revisit some of these examples once we have talked a little bit more about the important formulas relating to the Poisson distribution. The formula to calculate probabilities using the Poisson distribution is p of x equals e to the negative lambda power times lambda to the x power divided by x factorial. By plugging values for x into this formula, we can calculate probabilities related to the Poisson distribution. Now, you may be familiar with E, which is just Euler's number, and is approximately equal to 2.718. The E symbol can be found on most calculators. The symbol after the x is factorial, and tells us to begin with x and multiply the decreasing whole numbers together, beginning with x, until we reach 1. For example, 5 factorial is equal to 5 times 4 times 3 times 2 times 1, which is equal to 120. The mean of the Poisson distribution is lambda, and will be given in most problems, or you may need to do a simple calculation to find lambda, which we will discuss in one of the examples. The standard deviation of the Poisson distribution is just the square root of lambda. This notation means that x follows a Poisson distribution with a mean of lambda, meaning the event happens an average of lambda times in the specified interval of time or area. Just like with the binomial and geometric distributions, the Poisson distribution has TI-84 calculator functions that can be used instead of the formula. Poisson PDF calculates the probability x is equal to some constant a, and will give the exact same output as plugging in a value of x into the formula. Poisson CDF calculates the probability x is less than or equal to some constant a, and is equivalent to plugging in all values of x into the formula less than or equal to the specified number and adding them together. Let's take a look at some examples. A hardware store knows that, on average, 5 customers enter the store in a 20-minute period. Let x represent the number of customers who enter the store in a 20-minute period. X follows a Poisson distribution with lambda equals 5. Remember that the parameter lambda in the Poisson distribution is just the mean, which is why lambda is equal to 5. What are the individual probabilities that either 0, 1, 2, 3, or 4 customers visit the store in a 20-minute period? This is equivalent to asking for the probability x equals 0, the probability x equals 1, etc., all the way through 4. We could use the formula from earlier 5 times, plugging in x equals 0, 1, 2, 3, and 4 with lambda equals 5, but we will use the TI-84 calculator instead, as it's a bit quicker and easier to use. On the calculator, press second, vars, to get to the distribution menu. Scroll up until you see Poisson PDF. This is the function that finds the probability x is equal to some value, which is what we are trying to solve for. Enter 5 for the average of 5 customers as lambda, and 0 as x. The answer is 0.0067. There is about a 0.67% chance that no customers will enter the store in a 20-minute period. If we press second enter, we can bring up our answer and change 0 to 1 to calculate the probability of one customer entering the store in a 20-minute period, which comes to 0.0337. We can do this 3 more times to get the remaining probabilities. These probabilities turn out to be 0.0842, 0.1404, and 0.1755. What is the probability that at most 4 customers enter the store in a 20-minute period? Well, that's just the probability x is less than or equal to 4. We could just add up the 5 probabilities we saw for a moment ago, as they represent all outcomes where x is less than or equal to 4. 0.0067 plus 0.0337 plus 0.0842 plus 0.1404 plus 0.1755 equals 0.4405. Alternatively, and a bit more efficiently, we could use the Poisson CDF function in the calculator to calculate this value all at once. Remember that the CDF function calculates less than or equal to probabilities. So when we plug 4 in for the second argument of x, we get the probability x is less than or equal to 4, which is 0.4405. In the calculator, press second, vars, to get to the distribution menu. Scroll up and select Poisson CDF. Enter 5 for lambda and 4 for x. We get 0.4405 rounded to 4 decimal places, the same number we got when we added the probabilities up individually. There is about a 44.05% chance that between 0 and 4 customers enter the store in a 20-minute period. Let's try one more example. Consider a book that is being edited. We might know that on average, the book has 4 grammatical errors for every 50 pages. This is the case where the mean number of observations does not occur over time, but over space or area, or more specifically here, over a specified number of pages. Sometimes we might not want to calculate probabilities related to the segment for which the mean was specified in the problem. Suppose the entire book is 300 pages long. In that case, we might want to calculate probabilities related to the number of grammatical errors in the entire 300-page book, not just in a 50-page segment. In that case, we can do a simple conversion. We know there's an average of 4 grammatical errors per 50 pages. 300 divided by 50 is 6, meaning that a 300-page book is 6 times longer than a 50-page segment. We can take the mean of 4 grammatical errors in the 50-page segment and multiply by 6 to get an expected 24 errors in a 300-page book. So if x represents the number of grammatical errors not in 50 pages, but in an entire 300-page book, then x follows a Poisson distribution with a mean number of errors of lambda equals 24. Once you have done that calculation, you can calculate probabilities just like we did last time. For example, what is the probability that at least 35 grammatical errors are found in a 300-page book? Well, that's just the probability x is greater than or equal to 35. Recall that our Poisson functions in the calculator only calculate the probability x is equal to some specified value with the Poisson PDF, or the probability x is less than or equal to some specified value with Poisson CDF. How might we calculate the probability x is greater than or equal to some value? The answer is to use the complement rule, which says we can take 1, which represents 100% of the probability, and subtract off the outcomes in the complement, the outcomes not part of our event, and then we will be left with the probability that we want. Our event is greater than or equal to 35, so the complement is less than or equal to 34. We take 1 and subtract the complement to get the probability that x is greater than or equal to 35. We can use the Poisson CDF function to solve for the probability x is less than or equal to 34. We have 1 minus Poisson CDF 24, 34, which is equal to 0.0206. There is a 2.06% chance that there are at least 35 errors in the entire 300-page book. All right, my friends, that wraps up our discussion of the Poisson distribution. We will be exploring many more fun and exciting statistical topics that you won't want to miss, so make sure to check out our other videos.